And I wanted to just talk a couple of minutes about relativity because it's a beautiful piece of science. And it's very sort of important at the moment because there was a beautiful experiment done about 2 weeks ago now. The results were announced, which confirmed for the first time with very, 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 very high precision, so the highest precision confirmation we've ever had, that Einstein was not wrong. Right? His theory of gravity stood the test of the most precise experiment we'd ever been able to do. And I wanted to just show you a little bit about the results of that experiment. They were reported only 2 weeks ago. It was an experiment that was actually thought of back in the 1960s. So some of these scientists have been working for their whole careers, 50 years, on getting these results out. But relativity first. There's a very beautiful and easy way of describing what it is. Here's Albert Einstein. Einstein was a genius because he thought very simply, often in pictures, about how the world works. And what fascinated him back in the early 20th century, so in 1905 or so, was a result from a Scottish physicist called James Clerk Maxwell, who predicted, although he didn't know it really at the time, but he predicted that light travels at the same speed no matter how you look at it. So it's a bit of an odd thing to predict that. Essentially, what I'm saying is if I fly to that spotlight now at the speed of light, or let's say 75% the speed of light, and go flying towards that light, the light will hit me in the face at the speed of light. Not twice the speed of light, or 1.75 times the speed of light, but the speed of light. It's a very odd thing to predict. But that came out of the theoretical physics of the 19th century, from experiments on electricity and magnetism. Einstein was the first person to take that genuinely seriously and say, what does it imply? What happens if I say nature does work like that? So no matter how I move relative to you, we all agree on the speed of light. Well, he came up with a beautiful so-called thought experiment to work that out, and I can tell you that in about a minute, and it's the heart of relativity. He thought of this thing called a light clock. So imagine that I've got a very strange kind of clock, which is just two mirrors sat there like that. And my pendulum is light bouncing between the mirrors. So we can imagine 1 tick, 2 ticks, 1 second, 2 seconds, 3 seconds. It works as a very accurate clock. But remember that we've agreed that we all agree on what the speed of light is, no matter how anyone moves around. So what happens if I get this clock, literally on this stage, and I just walk along the stage? What do you see? Right? You see the clock ticking, but because I'm moving, you see something that looks more like that, because I started off over there and I walked over here. So the light, from your perspective, bounced along like that in a triangle. What does that imply? Well, if it's really true that we both agree on the speed of light, we both think it's the same, then you see my clock run slower than I do. Why? Because the light had to travel further to make 1 tick than it did when it was standing still. So that's a prediction. It's a very strange prediction. It says that moving clocks run slow. Time slows down when you move, from your perspective, watching me move along the stage. That turns out to be right. It turns out to be true. And in fact, the factor by which it slows down, which is given by this little equation here, you can work out using Pythagoras. And the reason I show the equation is because you might just be able to see, if you know the square of the hypotenuse is equal to the sum of the squares of the other two sides, you know that, you might just be able to see that, the squares and the square roots and things in here. When you just work it out, that's the answer you get. That's fascinating because that equation is built into the satellite navigation system. So when you get into your car and you set a satellite navigation and off you go, then the satellite navigation system works basically by measuring time differences between clocks on satellites and clocks on the ground. The satellites are moving relative to the ground and they're high up, so gravity's a bit weaker. Turns out that means time passes at a different rate. How much? Well, Einstein predicted 100 years ago that it would shift by 36,000 nanoseconds per day. A nanosecond is 1,000 millionth of a second. That doesn't sound like very much, 36,000 nanoseconds. But light travels 30 centimeters in a nanosecond. So that means that the satellite navigation system would drift by 36,000 lots of 30 centimeters in its position measurement. It's about 10 kilometers. So the satellite navigation position would change by 10 kilometers a day if you didn't take account of that, which Einstein works out in 1905 by thinking about a light clock with 2 mirrors. Beautiful bit of physics, and it found its application a century later in satellite navigation.